Okay, now let's look at what is involved in recursive partitioning. So in recursive partitioning, we pick one predictor variable. So you may have a bunch of predictor variables. So like in the example that we saw, income and credit card expenditure and so on. So there, for example, you select income. Okay, and then you select a value to partition. So pick one predictor value and then pick a value of that predictor variable. So in this case, if you select income, then you may select a value of 100,000 as a value to split. So now you take the training data and then split the data into two parts, one part containing all observations with income less than the limit, okay, the 100,000. On the other side, anything exceeding that S sub I value. Okay. So by including the equal to sign on one side and not the other, you get a clean break. Okay. Mutually exclusive partition. Okay. So take each part and then further split with the same predictor or with a different predictor. Repeat until the part partitions are maximally homogeneous. Okay. So here is an example of riding mower. So you have income and lot size as the two predictors, and the target is ownership of riding lawn mower, owner or non-owner. Right. So how to split? Okay. Order the records according to one variable, say lot size. So take lot size and then sort the lot size from smallest to the largest. It turns out that the smallest is 14.0 and the next higher value is 14.8. So you can, one way of doing this is to take a midway point between the two, and then in which case you don't have to include the equal to sign on either side. So because it'll split the data into mutually exclusive partitions. But if you want to take one of the limits, like for example 14.8, then you will have less than 14.8 on one side and greater than or equal to 14.8 on the other side. So you'll have a partition like that. Now once you have a partition, then you have to evaluate that split. How good is that split? And we will talk about how to evaluate how good a split is in a little bit. Now, so now you have one split. So that's one candidate for split. Then you take the next candidate. So next candidate will be anything, you have to go to the next higher value after 14.8, and that I believe is 16. So anything less than 16 on one side, on the left side, and greater than or equal to 16 on the right side. So that would be the next candidate for split. So you continue this for all possible splits of lot size. So now you have all the possible split candidates based on lot size as the predictor. We'll do the same thing with income. Okay. Start from the smallest value and keep working, and you have a bunch of candidates for split based on the second predictor, which is income. So for each possible split, you will have a performance measure. Okay, how good is that split? And we'll talk about those measures a little bit later. So let's look at the how the splits actually work. So here, suppose if the first split is lot size 19,000, so everything less than 19,000 on one side, everything above or greater than or equal to 19,000 on the other side, and then you see is mostly owner, but there are some non-owners. So there is some impurity here. This is not completely homogeneous. And again, on this side you have mostly non-owners and 3 owners. Again, this is quite homogeneous but not perfect. There is some impurity on this side. So you split now a second split, okay, based on income. So now we have this side of the first split has been split into two parts. So now we have completely homogeneous here. So no further split is necessary from this rectangle. Whereas here it is almost homogeneous, except there is one owner here. So it is somewhat, it's not completely pure. There is some impurity, a little bit. And then you further split, maybe you need some splits here, and split here, and keep going, okay, until you reach a point where you get all pure rectangles. Okay, of course, when we split up to, when we branch it up to this level, then you're actually coming up with a rule set that works very well for this particular data, and it may not generalize well for new data. So we are fitting everything, a signal as well as the noise that is peculiar to this particular data set. So that's not a good thing. So you have to back up and prune the decision tree so that you get a tree, a set of rules that will generalize well for new data as well. And then how do you choose? Now you have a whole bunch of possible candidates for split, okay, a bunch of them from the first predictor, bunch of them from the second predictor. So now you select the best, okay, measure how pure or homogeneous each of these parts are, and then you select the select the x sub j and x sub j and s sub j that gives you maximum purity. Okay, so select the candidate that gives you maximum purity, and then use that to split, and then you go back and repeat, and so on.